Hello Internet, I am Alex from Barefaced and this is part 2 of a course called Sound for Musicians, where we're trying to demystify basically how it all works, and particularly from a context of musicians and particularly guitarists and bassists, because that is what I do and that is what we do here at Barefaced. So, waves. Sound is a wave. It's a longitudinal wave, so it's not an uppy-downy wave. This is called a transverse wave, where the wave motion is across the direction of travel of the wave. It's a longitudinal wave. It goes in the same direction that the wave is travelling. And it works through compression and rarefaction. So compression, the push, and then rarefaction, the pull of a wave. And that's why speakers move how they do. You see them move in, my drum skins vibrate, That's how sound works. But because it's a wave, it doesn't move in an entirely intuitive way. Most people seem to get confused about this, and there are two sort of mistakes made when it comes to how waves behave. One mistake, in one direction, is to think it's like a laser beam, like sound just goes where it's pointed. So if a speaker's pointing at you or a sound source is pointing at you, sound is going in that direction, sound is coming out from there. And that's definitely not the case. The other mistake people make is that they think sound just goes everywhere. If something's making sound, it goes everywhere. Like, say it was heat conducting out of something, it just goes in all directions equally. It doesn't do that either. And I suppose that the third way people look at it, which is a bit close to reality, is that the sound comes from the side. You're looking at something, which again, it doesn't do, but that's closer than the other two things. So what does sound do? Well, it comes from our source, and how it moves from a source varies. But then once it's moved from the source, there are 4 ways that the motion of the sound can be modified. So the first one is refraction. So that refraction is where a wave bends. Right now. So this is probably the least important one when it comes to talking about sound waves, but it's quite an interesting one. You will not generally be able to do anything about refraction related stuff because it's part of the physical world messing with things. But we're going to drill into these separately now. So we've got refraction, so that's a wave being bent. The sort of refraction you will most be familiar with is when you look into something in the water. So you're in air, you look into something underwater, and it's kind of in the wrong place. Refraction, so if you're at an aquarium, refraction tends to, I think, makes the fish look bigger than they actually are. Or the classic one is if you are a fisherman, you look down at where you think a fish is, and it's actually somewhere else because the light wave is bending. So it's that sort of thing, but we're doing it with sound waves. Diffraction, now that is, it's the effect of objects to bend and redirect a sound wave. It's not caused by the way they're travelling through something, it's about the way they're going around something. So either not through a change of medium, so not like a change from hot air to cold air, but say through a gap between a solid object that doesn't let sound through the actual solid object, or around a corner. So we hear that all the time. That's why we can talk to someone in the next room, that the sound just goes through the door and diffracts around the corner. Then reflection, well, we used reflection with light, that's a very common one with mirrors and such like. I'm going to zoom out a bit, that's feeling a bit intense there. But sound reflections, we hear that all the time, and the most obvious way we hear sound reflections is in the change of an acoustic space. We all know that being outdoors sounds different to being indoors. We know that being in a big echoey room, echo is a sound reflection, full of hard surfaces causes lots of reflections, whilst a small cosy room with heavy curtains and thick carpets and soft furnishings, it sounds dead. There's fewer reflections, and the reflections that do happen are closer together rather than a long reflection which stands out as an echo, so it separates out. And then the fourth one, superposition and interference. This is quite mind-bending, but really critical. So if you have 2 identical sound waves, equal loudness, equal frequency, so they're identical, but one is the reverse, so it's inverted polarity, 180 degrees out of phase, and they meet like that, they will totally cancel. That is how noise cancelling headphones work. They try to listen out for sounds and then generate the opposite sound. And they, as we know, they don't work perfectly, but they do make things an awful lot quieter. So that is what we call interference. So that is two sound waves meeting, interfering in such a way they destroy each other to a degree. Superposition is the same thing, but when things are adding, or a mix of adding and subtracting. And superposition is pretty amazing, because if you ever look at a sound wave that has been recorded and then displayed on a TV screen, a computer, something like that, so you actually see the visual interpretation of a sound wave, which does show it as a transverse wave, so it's a wiggly line like that, it's not a forwards and backwards thing. That sound wave can be built out of lots of other sounds. So if you put a sine wave on top of another sine wave, you get a more complicated sine wave, and when there are different frequencies, it sort of separates out. So you can end up with a very complicated wave shape. It's all built out of other waves, and that is superposition. And what's really cool about superposition is you can put those all together, it makes one complicated wave, and your brain can separate all those out. You can hear a whole orchestra and pick out different instruments individually. So that's the brain deconstructing the superposition of the sound. So there we go. This is how waves interact. They refract through changes of medium, they diffract around things and through things that they're not actually passing, that's not transferring the sound, so solid objects that are essentially rigid. Superposition interference, so that's how they add and subtract, and reflection, again, how they bounce off things. We'll drill into that more thoroughly in a moment. Well, I say in a moment for me, later for you, or maybe immediately, depends when you watch it. Thank you, I've been Alex from Barefaced, and this is Sound for Musicians, Part 2. There'll be a few more parts. Thank you and goodbye.